Hello, and welcome to Starting Out with Quantum Computing. I'm your host, Lloyd, and I think I've got an interesting one for you this time. So, this is the start of a new video series, and the point of this video series is that I want to discuss the foundational aspects of quantum computing, and I want it to be a sort of lecture style video where we can take the viewer from a foundational level and level up their knowledge in quantum computing. But before we even start to talk about quantum computing, we have to know what the word quantum even means. We have to go back a bit in time and understand what quantum theories are and what quantum mechanics describes. So this is the first video in this series, and we're going to be discussing what is quantum. And you can access these videos either from YouTube or from my Substack. And you can also listen to the podcast version on the normal platforms such as Spotify or Apple Podcasts. Without further ado, let's just go straight in. So we always have to start with a definition. What does the word quantum mean? And it basically just means the fundamentally smallest thing or property involved in any sort of interaction that we can describe in the universe. So it means it always details as the smallest scale possible. So for example, let's think about light. Let's think about photons, which are the carriers of light. And they are indivisible. You could not chop them in half. It's not possible. And so we can say, therefore, that a photon is a quantum of light. It is the smallest possible thing, smallest possible particle of light. Then we have another word that naturally follows, which is quantized. And it basically means that it can only occur at specific values. So for the mathematicians, they would like to use the word discrete here. So think, for example, you could have one sheep, you could have two sheep, but you couldn't have 1.5 sheep. That wouldn't make sense. And the same applies for things in physics which are quantized. And so the German physicist and Nobel Prize winner Max Planck coined the term quantum in a famous paper over 100 years ago. And so therefore it naturally follows that quantum mechanics is simply just the field of studying how systems work at the smallest scales, how they work and operate in the quantum world. So that is all quantum mechanics really is. Doesn't make it simple, but it's simple to understand what it describes. So let's talk about the beginning of quantum mechanics, and you could arguably say that it was sort of kick-started by Sir Isaac Newton in 1670, who came up with his corpuscular theory of light. And what he was saying is that light is made up of these indivisible packets called corpuscles, and corpuscles can travel in a straight line, and they will possess some sort of motional energy, some kinetic energy. And it was a very good theory, and Sir Isaac Newton could easily observe reflection, for example. So we have a reflective surface, the light will hit it at some angle and it will reflect at that same angle. So if it hits it at 30 degrees, then if you drew a line going straight up from where the angle it hit it, it would simply just reflect 30 degrees in another 30 degrees in the continuing direction. And if light went straight down, completely 90 degrees to the surface, it would go completely 90 degrees back up again. And the other idea was refraction. And so this is a phenomena that occurs when you have two different mediums and you have light, or two different materials, you can think of it like, and you have light that is leaving one and entering another. So think about it. If you have a fork or a spoon in a cup of water, you notice that the spoon is deformed and the handle kind of disconnects from where it is outside of the water. And this is because of refraction. What happens is, as light travels from one medium to another, it changes direction. It's quite an interesting phenomenon, and it makes things look different in water from where they truly are when looking from the surface. So we've kind of, I suppose in the sense, Sir Isaac Newton had kind of touched upon the idea that things could be made divisible, and the sort of quest here was to see, well, what's happening at the smallest of levels? You know, I know as a human that I'm made up of cells, I've got skin cells, but what makes up those cells? And then what makes up that thing? And what makes up that thing? What is the smallest Lego brick in the universe? And so in the 1800s, Sir J.J. Thomson would develop one of the first atomic models, believing that atoms make up they are the fundamental building blocks of the universe. And so he called his model the plum pudding model. And the way it works is the pudding part is the large sphere in the exterior, and it's a sphere of positive charge. So this means that you have this huge kind of positive charge spread across this entire sphere, and then on the inside you have the plums, and these are electrons. And Thomas argued that we could call this a sea of electrons, and that they would be evenly dispersed about this pudding, about this spherical positive charge, in order to make sure that the charges were balanced all the time. And this was proven wrong, but at the time it was seen to be a very good guess, but it was proven wrong by Rutherford. And so Rutherford was another scientist, and he did an experiment called the gold foil experiment, and it is taught in secondary school to this day. And so what he did is he basically shone this particle source, which he knew would be positive. He knew it would be positive, and he shone it, or he basically allowed it to hit these gold atoms, gold foil. So this would have been, back in the time, everyone was using gold foil and gold leaves for painting and stuff like this. So it would have been an easily accessible material, and he shone it at the gold foil. And if Thomson's model was correct, what would have happened is that the sort of evenly dispersed positive charge shouldn't have been enough to change the direction of the incoming positive particles. However, what Rutherford noticed, along with his team of students, is that there was some scattering going on. So you can kind of see here that what's happened is that there comes a point where the positive particles that are incoming get scattered. And you can literally see from this other photo here that is exactly what's happening, that the alpha particle, which is this charged particle that comes out of the source, changes direction. And what that means, therefore, and what Rutherford argued, is that there must be a very dense center of positive charge, and there must be basically no positive charge anywhere else. So yes, the positive charge had to be more concentrated, it had to be in the center, and it had to be about 10,000 times smaller than the entire atom, which was a revolutionary thought. And this center should also contain the majority of the mass of the atom. So the electrons themselves would not have much mass, it would mainly be the nucleus. And these types of experiments are known as particle scattering experiments, and the experiments that we have today, where we do particle scattering, would have been originally based on Rutherford's experiment, and they're now commonly used in experimental particle physics across the entire world. And after the nucleus, which was coined by Rutherford, he said that this positive center of charge, we're going to call it the nucleus, became accepted, nuclear physics was born. And so now we need to talk about old quantum theory, which was beginning in the 1900s. So once we've discovered what a nucleus is, we started to, as humans, started to get closer and closer to the mystery of what's happening at the smallest of scales. So Max Planck, very famous physicist, came up with a law to explain black body radiation. So what is black body radiation, I hear you say? And imagine you're putting a poker into a hot fire, and you notice that the colour of the poker changes over time. So first it might start out as kind of a small glow, then it will go from red to orange, then it might go from orange to yellow, and if you left it in there for a really long time, it might even start to go white. So this is what we call black body radiation, basically. It's the idea that objects emit radiation, emit light of different frequencies when they are heated. And yes, as we said, the object starts to emit this thermal radiation due to heating, and what we had sort of discovered originally is that in the classical theory, so I'd like you to take a look at the black line first. In the classical theory, we kind of thought that, okay, well, as we increase the temperature of whatever body we care about, this will affect the frequency of the light. But the classical theory was saying that there's no limit to the frequencies that are emitted as we increase the temperature. So for example, at 5,000 Kelvin, which isn't actually that hot, it was saying that essentially the brightness of the object would be infinite. But that couldn't be possible, right? Because if at 5,000 Kelvin the brightness of an object was infinite, that would mean that we could literally never look at the stars, we could never look at the sun. It would be so bright that everything would be a white light and we wouldn't be able to see any other color other than white. We would be blinded eternally. And that's not the case. What was discovered later on is these beautiful curves here, the blue curve, the green curve, the red curve, that at different temperatures objects will emit a large spectrum of colors, and both into the UV region, ultraviolet region, both also into the infrared region, but there will be a dominant peak, and that the height of the peak will be at a color. So we will mainly see that color. So what we're saying is that at 5,000 Kelvin, for example, we'll mainly see yellow. We might see a bit of green, and as we get hotter, we might enter the blue, and we might enter other colors. And we have actually a lot of colors here, so it's most likely to look like a combination, maybe starting to get towards white, etc. But that is the theory. And what made this theory quantum? And so Max Planck said, okay, well, I need to mathematically describe this. So let's say that these atoms are like harmonic oscillators. So we are going to explain what harmonic oscillators are, so bear with me for just a second. But let's say that these atoms are like harmonic oscillators, and let's assume that each oscillator could only emit a limited and certain amount of energy, thermal energy, at a certain frequency. This would mean that since they can only emit certain values of energy, this means that the energy they emit is quantized, and therefore he came up with an equation to describe the quantized energy that these harmonic oscillators could emit. And for this he got a Nobel Prize in physics for the discovery of energy quanta. And the reason he got a Nobel Prize, or one of the reasons of many, is the idea that his mathematical model, by treating them as harmonic oscillators that could only emit a limited amount of energy, that fixed the problem of the ultraviolet catastrophe that we were talking about earlier, where we were saying that the original theory was saying that at a certain temperature it's going to be infinitely bright and it's going to emit infinite energy, and that's just not plausible or possible. This mathematical model solved that. So yes, he deserved a Nobel Prize for it. So what is a harmonic oscillator? So it's kind of like a spring. I think that's the easiest way to describe it. It goes up and down, and there is an equilibrium point. Let's imagine you actually had a spring or a slinky Is it going to continue to come up and down forever and never stop? No. There's an equilibrium point where it will stop at. So that is a harmonic oscillator. Anything that can move up and down and experiences a force proportional to how far it's been displaced from its most comfortable state. And we call that most comfortable state the equilibrium. So if you want a very formal definition, you can say it's any system that, when displaced from this equilibrium, will experience a restoring force to bring it back. And it's useful because in physics, anything that is subject to a force and anything that has an equilibrium that it wants to go back to, we can describe it like a harmonic oscillator, and we can use the maths and the intuition of harmonic oscillators and apply it to that specific problem. So, for example, we can describe vibrating molecules. We can describe the sway of a branch. We could describe a pendulum moving, the way that the clock hand sways in old and large clocks. These are all things that we can describe using this type of mathematical formalism. What is it in the quantum side, though? Because Max Planck was a little bit advanced. He wasn't talking about a classical oscillator, harmonic oscillator, like a spring. He was genuinely talking about a quantum harmonic oscillator. And the reason you know this is because he was saying that the energy levels that these harmonic oscillators can thermally radiate were quantized. They were discrete. It wasn't just any sort of energy that these harmonic oscillators could emit. It was only certain frequencies and certain energies. So that makes it quantum, because it's quantized. And this is kind of what a quantum harmonic oscillator could look like. So it's a little complex, but you can notice that in a lot of these, they're kind of coming from one point and going back to equilibrium, going back to another. So they're oscillating between the equilibrium points. They look a bit like strings, if you will, but they are a little bit complex. They describe the quantum. They are the quantum equivalent of the classical harmonic oscillator. That's the important thing to understand, rather than what they actually look like. And therefore, we can basically model these oscillating things, these quantum things, which they are actually formally known as wave functions, and we will go into what that is in just a bit. But we can think of them as they are wave functions, and we can model any quantum system as having this sort of harmonic oscillator wave function, and it will then obey those same properties, just in the quantum way. So if we want to think about a quantum harmonic oscillator, we have to think about oscillating wave functions. And these resulting wave functions will have quantized energy levels. So what that means is that, as we spoke about before, just the same way that you can only have you can't have 1.5 sheep, you will only have certain energy levels that these quantum harmonic oscillators can be in. And it can be very useful. The quantum harmonic oscillator can be useful for lattice vibrations. It can be useful for photons. As we spoke about earlier, photons are the quantum of light. They are the smallest particle, the indivisible particle responsible for light. Atoms that are trapped. So we might want to take an atom, we might want to trap it in a certain area using some sort of field or force, and that can be useful to use quantum harmonic oscillator formalisms. Quantum fields, this is another one that is important, and we will talk about this later. And it is useful in quantum computing as well.